So we said that we can never get the true value of any measurement. We try to get it as close as possible to the true value, but there will always be some uncertainty. You can never draw your conclusion with 100% confidence, but you try to get it as, but there will be some degree of confidence. So this is because there will always be an error in your measurement. And you can express this error with confidence or with uncertainty that usually have the positive and negative sign. There are two types of errors that you may encounter in any measurement. These are the random error and systematic error. So what is the random error? The random error is called the indeterminate error, and it affects the precision or reproducibility of a result. Usually the random error arises from uncontrolled or uncontrollable variable in your measurement. So you cannot control the random error, you cannot correct it, and it will always be there. It's something you don't have control over, and it will always be there, and it will always have a possibility of being positive or negative. So in one measurement, it might be positive, in another, when you repeat your experiment, it might be on the negative side. This is why it affects the reproducibility, not the accuracy of your measurement, but the reproducibility or the precision of your measurement. Um, uh, as we said, it will always be there and we cannot correct it. An example of that is the random error associated with reading a scale. So when you read a scale, not because the scale is not calibrated or there is a problem with it, but because when you read it, there is always a possibility that it might be a little bit higher than it should be or a little bit lower than it should be. This is the random error. The other type of error is the systematic error. So the systematic error is called the determinate error, and it affects the accuracy of your measurement. Accuracy is nearness to the true value. The systematic error is different from the random error because the systematic error can be corrected. It's something that indicate some sort of a problem in your measurement or in your experiment, and you need to correct that before you actually draw your conclusion or before you can actually say what is the result of your measurement. Um, this kind of error is reproducible, which means it will always be shifted towards one end. It's either positive all the time or negative all the time, and it has a fixed value. So um, you need to correct that before you actually can get your actual result. This is why it affects your accuracy. An example of that is the incorrectly standardized pH meter. So if the pH meter is wrongly calibrated wrongly, so for example, it should, for example, if you use a buffer that is used to standardize the meter, if the pH of the buffer used to standardize the meter is 7, but it really is 7.08, then the pH reading will always be 0.08 pH unit too low, which means you should have been using a buffer that has a pH of 7, but instead you used a buffer that the pH of it is 7.08. So when you standardized your pH meter, you standardized it wrongly. So now for any pH measurement, you're going to measure using this pH meter, always the pH you're going to get is going to be 0.08 lower than the actual one. So this is a systematic error, and we should eliminate this error. And as you see, it's always shifted towards one end. So in this example, it's shifted towards the negative end. It will give you a result lower than the actual one. So you have to eliminate this systematic error before you actually can say this is my results and before you draw your conclusion. So how can we what are the different types of systematic errors? There are three types of systematic errors. The first one is instrumental errors. The instrumental errors are caused by non-ideal instrument behavior. So as the example we said, faulty calibration, like we did last time in the example we saw with the pH meter. So this is going to be instrumental error because there is a problem with the calibration of the instrument. Or maybe we use the instrument under inappropriate conditions. So if you change the condition and the conditions of using the instrument is inappropriate for your experiment, then the behavior of the instrument will be different and the results is going to be different. The second type is the method error. So method error, it's because of or arise from non-ideal chemical or physical behavior of an analytical system. An example of that, for example, if you are doing some sort of analysis and you are trying to find the quantity of any element in a solution, for example, and to do your analysis, you need to adjust the pH to a certain value. So if you don't adjust it to the proper value, or if you adjust it to a different value than the one that is ideal for your method, then you're going to get a different result. You're not going to get the proper one. So this is the method error. So there is a problem in the method itself. And every time you repeat your method, as long as you follow the same protocol you have been followed with the same error, you're going to get the same result, but with the systematic error. The third type is the personal error. So personal error is the error you can encounter yourself. This is because of carelessness, inattention, or because of personal limitations of the experimenter. So the person who does the experiment doesn't have enough experience, or his carelessness. So for example, if you should make a solution that is 20 mil and then you didn't make it to 20, you made it to 21 mil, 23. So it's carelessness. You should add the different reagent in certain order, but you didn't care. So in one time you added it in that order, in the second time you added it in a different order. This is a personal error. Personal error will definitely affect your result, and if every time you do a different error, then it's going to not only to affect your accuracy, but it will also affect the precision of your result. So how can we detect systematic errors? Um, as we said, that systematic error will mostly affect the accuracy. And if the systematic error is there and we keep repeating the same error every time, you're going to get the same results every time. So it's going to be reproducible. You may think that you did it the right way because you're still getting the right answer every time, or the same results every time. So you think it's not an error, it's correct. But in order to detect the systematic error, there are 5 things you can do. The first one is to analyze a known sample, such as a certified reference material. So if you have a standard solution that you know that it should have a certain concentration of a certain material you are analyzing, and when you analyze it, you get a completely different result from the one you should have, then you should know that there is a systematic error in your method. It doesn't have to be personal or specifically method or instrumental. It can be a combination of the three, or it could be one of these 3 types. So once you get a result different from the one you should get, then you should know that there is a systematic error in your analysis. A second thing is when you analyze a blank sample, and a blank sample is a sample that doesn't have any of your analyte. So if you analyze an analyte sample and you get some reading higher than you should, so you should get a reading of 0 when you analyze a blank sample. So if you get something that indicates that you have your analyte, then there must be some systematic error in your method because you shouldn't get this result. A third method to detect the systematic error is to use different analytical method to measure the same quantity. So when you use different method to analyze or measure the same quantity, you should get the same result every time. If you get different results, then there must be systematic error in one or more of these methods. So you should always know which one has the systematic error. For example, if you analyze the same sample with 4 different methods, 3 of them were in agreement and one was different, then this one in particular will have some systematic error, and you should know what is the systematic error and try to eliminate it. Another method to detect the systematic error is use the round-robin experiment. So use different people in several laboratories to analyze identical sample by the same or different methods. So if you get the same sample, like a certified reference material or anything, or it can be done without knowing the actual concentration, and you get different people from different laboratory to analyze this sample. They all should have some kind of agreement in between them, whether they use the same method or different method. So if there is no agreement with one or two of these results, there must be some systematic error in this method. Generally speaking, any disagreement beyond the estimated random error is systematic error. So if I know that there is a random error plus or minus certain value for this measurement, and I get a different value, whether it's higher or lower, then there must be some sort of systematic error. So the kind of error that we express as uncertainty for our experiments is the random errors. So we can always estimate or measure the random error associated with our measurement. Uh, we normally express the random error as standard deviation or standard deviation of mean or a confidence interval. We will discuss all of these uncertainty terms in the next lecture. And always be careful, because when we do that, we have to assume that systematic errors have been detected and corrected. So the error that you express is merely for the random error. The uncertainty is only for random error, not for systematic and random errors. There are two types of uncertainty. We can express it as absolute uncertainty or relative uncertainty. So the absolute uncertainty expresses the margin of uncertainty associated with a measurement. For example, if the estimated uncertainty in a reading of a calibrated burette is plus or minus 0.02 mil, then for every reading you get from this burette, there will always be some error that is 0 plus or minus 0.02 mil. So it's absolute uncertainty, and whatever the volume or whatever the measurement you get from this burette, there will always be that specific error within your measurement. It can be anywhere in between these two values, plus or minus 0.02 of your actual measurement. Relative uncertainty, it compares the size of the absolute uncertainty with the size of its associated measurement. So, for example, the same burette has absolute uncertainty of 0.02 mil. Now you can have so many different measurements or so many different readings from your burette. If you have 1 mil reading from the burette, then the relative uncertainty here is going to be quite high, because relative uncertainty is the absolute uncertainty divided by the magnitude of your measurement. So it's going to be 0.02 divided by the 1 mil. So it's going to be quite high. But if you have a higher measurement, like 12.35 mil, for example, then the relative uncertainty here is going to be much less. So the higher the magnitude of the measurement, the lower the relative uncertainty. The relative uncertainty can be expressed as a percentage, and it's usually dimensionless, so there's no dimension for it. And unlike the absolute uncertainty, which have the same value as the measurement. So because it's relative, because it's a ratio between the absolute uncertainty and your actual value. So remember that the higher the value of your measurement, the lower the relative uncertainty of that